Okay, Assalamualaikum warahmatullahi wabarakatuh. So this video we're going to continue with the three-phase half-wave control rectifier, and on the screen now this is the session outcome. Right? After completing the session, the student shall be able to the same for, but now we apply to the three-phase half-wave control rectifier. Right. So let's look at the notes. Okay, so the three-phase control rectifier, before we look at the operating principle of the three-phase control rectifier, let's do some revision on the three-phase uncontrolled rectifier. Okay, so as the notations, please memorize, or just I think this is the notation that we've been used throughout the monograph, the lecture notes. So V phase, V peak phase, V line to line, as well as the V peak line to line. Right, and as for the half-wave rectifier, for the uncontrolled version, we have a 3 diodes connected to the phase voltage of red, yellow, blue. And then the important thing is we have this commutation angle of 30 degrees, because this is the point, the intersection between red and blue here actually determines the turn on of the red phase. This is the beginning of the red phase to turn on. Right? So this will be we call it a reference for the control rectifier, because this will be the point of zero firing angle. If you measure from the zero crossing of a red phase, from there to there, this is 30 degree, and that will be the firing angle, the firing angle of 0 degree for the red phase voltage thyristors. Okay, so to understand or to determine which diodes are on, we're going to apply this hints or tips whereby anode with highest potential will conduct. So this is the diode operations principle. Whichever supply voltage that is highest, then that phase diode at that phase will be turned on. And when this diode is turned on, the point of the output voltage will be connected to the supply voltage, and it will copy the phase voltage. Right? And therefore, finally, we found out that the output voltage copy or follows the envelope of the phase voltages. Okay, right. So now let's look at the half control or half wave control rectifier with resistive load. So we have red thyristors, yellow thyristors, and blue thyristors, and the angle of the firing angle, we apply only alpha, which is the firing angle, to the thyristor R, which is 30 alpha angle, and then we have yellow phase with alpha plus 120 degree, and blue phase with alpha plus 240 degree. So you only need to specify the firing angle for the thyristor R, and thyristor Y and thyristor B is just a matter of you need to add 120 degree and 240 degree respectively. Okay, so this is the circuit, and this is the real circuit connection, and this is the connection for your PSIM. Okay, if you use a PSIM, then you can use the three-phase supply voltage, and then you can also use the half-wave thyristors rectifier, the block set here. So you just apply on block set instead of discrete component. You can use the block set of the three-phase thyristors, and then you connect this as your alpha. Okay, I'm going to share with you the PSIM circuit of this, and just simulate it. Right, and this is the angle of firing angle. Okay, so you just simply change voltage here, and that will be the angle in degree. The angle is in degrees, so if the voltage is 20 degrees, which means alpha equals to 20 degrees. We compare red and blue because we know that the intersection between red and blue here will tell where is the alpha equals to 0 degrees. Right? So That's why we need this red and blue, so that this will be the reference point where alpha equals to 0. Okay, so actually there will be two cases. With a purely resistive loop, there will be two cases of current or output voltage, and I think I better show you the simulation. Okay, so I'm going to show you the simulation of the three-phase control half-wave control rectifier. Right? So we start with alpha equals to 0. So when alpha equals to 0, that is very much equals to the diode operations, isn't it? Right? So we go and run the simulation. Alright, so that will be your output voltage. Okay? The output voltage is similar to the diode waveforms. If I can put in the red, yellow, and blue, so that will be the red, yellow, and blue. And this VDC will be actually, if I can put that on the, okay, going to make it bold. So that is your output voltage. You will copy the envelope of the supply phase voltage. Okay, right. So let's delete this. Right. So now let's change the alpha. So we start with alpha equals to 20 degree. Okay, so when you set alpha equals to 20 degree, so we understand that for the thyristor yellow, there will be 120 degree plus 20, and for the blue phase, there will be 240 plus 30 degree. Okay, now summation. Then that is your waveform now. I can show you the path. So this is the path of the phase voltage. So now I can actually change that to want only short pass. So I'm going to change that to short pass. So 50 Hz, 2 degree for the short pass. And let's see it again. There you are. So that is the pass for that's the one. And then when it trigger, then your voltage is copy the output voltage, isn't it? Now copy the supply voltage. Okay, and then we still and then we continue to simulate again to, let's say, 30 degree. Run the circuit again, and now we can see that the phase voltage now, the output voltage now touch the zero level, isn't it? It touches the zero levels here. If you can see carefully, it touched the zero voltage here when alpha equals to 30 degree. Okay, so what happens if alpha is beyond that 30 degree? So from there, there is 30 degree. Isn't it? Right, there is a 30 degree. So what happens if alpha greater than 30 degree? Let's do the simulation. Don't worry. Get to simulate again. Get to change that to 40 or 50 degree, which is beyond than 30 degree. Run the simulation again. Look at that. Now there is a, if you look carefully, there is a discontinuous. The current become, or the output voltage become discontinuous. So just now you see that when alpha from in between 0 to 30 degree, your output voltage is continuous. Okay, but when your alpha is between 30 degree, so we have this is so from there to there is 120 degree. 30 degree here. There. So when your alpha is so you have alpha from there until there. So this is 30 degree until 150 degrees. Right? So we have 130. Okay, so we have this is 30 degree from there. This is 30 degree and until 150 degree. So if we change if alpha is in between 30 degree to 150 degree, you're going to see that the output voltage become discontinuous. So if I can try to this continuous again, and then if I increase the alpha, then it will follow that. So I can simulate again, like okay, simulate again. So let's increase to 100 degree. That is my output voltage. Okay, so it's always stop at this 150 degree here. Okay, change again until we reach 149 degree. Now it is 0, 3. So when you have alpha equals to 149, 150 degree in theory, then you see a 0 output voltage. Okay, so now we're going to analyze to get the output voltage equation for those cases. The first one will be the continuous case, and then the second one will be the discontinuous case. Alright, so now let's look at the waveform, the notes again. Okay, so for the first case, we have 0 to pi over 6. Right, so from 0 to pi over 6, and you can look at the waveform again. The current is or output is actually continuous, and the 3 pulse rectifier duration of each pulse is 2 pi over 3. Okay, duration of the pulse is almost 2 pi over 3, and if you think about the conduction of uh, the thyristor 1, so from there until here, isn't it? So that will be the thyristor R or thyristor 1. Red phase thyristor will operate from there, isn't it? And then we have thyristor yellow will operate from there to there. And then it's changed to blue there. So the output voltage is always continuous. Alright? So it is always continuous. Okay, so now we are interested in looking at the output voltage equation, the average output voltage equation. So what we need to do is we just take one part of it and we shift it. That's what we did for the diode rectifier. So we take only one pass, and then we're going to modify or switch or shift to the left so that we have 0 degree or 0 second at the peak of the voltage. So this will be your peak voltage point. Okay, and then now you know that it is 120 degree pulse. So this is 120 degree pulse, and now you are split into this will be, if I look at, I can show you, this is pi over 3, and again this is minus pi over 3, and this is pi over 3. Right. Because of that alpha, then we have to add. So this is your alpha, right? So now we have to add alpha plus minus pi over 3, which is minus pi over 3 plus alpha. So that will be your limit here. And then we have the upper limit, which is pi over 3 plus alpha. So this will be the upper limit if you want to do the integration. And again, when we switch or we shift to the left, so that it is at 0 second or 0 degree here, then this will be changed to v peak cos theta. Okay. The function now become v peak cos theta. So therefore, now the integration becomes that. So we have 1 over 2 pi over 3 because each pulse have 120 degree. So you have divided by 2 pi over 3. And then the lower limit will be minus pi over 3 plus pi minus alpha. Then we have pi over 3 plus alpha. Top, the top the upper limit, and then you have v big cos theta d theta. Right, and then you solve that and you found out that the VDC, the output voltage, the average of the output voltage becomes V peak or 3 multiplied by root 3 V phase divided by 2 pi cos alpha, or you want to represent it in terms of line to line, then it becomes 3 multiplied by V peak line to line over 2 pi cos alpha. Okay, so this is for the continuous operation. Right. They again, the two cases only happens when you have load equals to R, which is purely resistive load. You won't see this case when we have load in terms of inductive load R plus L, then there is no continuous or discontinuous. It's always continuous. Okay, so now it is only R. Okay, so you can try to derive the RMS. Yes, again, look at the waveform, try to find the RMS of this, because you need to find the VRMS of the output voltage. Okay, of the output. So again, you need to apply what? VRMS is always the root. Mean is 1 over 2 pi over 3. Then we have to integrate minus pi over 3 plus alpha plus alpha. And then you have V peak cos theta squared d theta. Just complete that, and then you can find what is VRMS, because in the question you can be asked the ripple factor, isn't it? So you need to find what is the VAC, because VAC equals to VRMS squared squared plus VDC squared, if I'm not mistaken. Okay, so to get the ripple factor, so you have to evaluate for VRMS by using that formula. So this is exercise for you. Try to find VRMS, and then you can use the PSIM to check your answer. Right? Check with PSIM. Alright. Okay. So now we're going to look at the case number 2, which is the discontinuous operation, whereby your alpha is in between. This is 30 degree gain, and then this is 150 degree. Okay? 150 degrees. So you see that the current is discontinuous, current or voltage becomes discontinuous, and what will be the average of this output voltage? Okay, so therefore we need to consider this pulse. Just take this pulse, since we know that it always stop at before that. Let us think about why we have this situation. Why there is a discontinuous of voltage when alpha beyond than 30 degree. Okay, so with that, I'm going to show you the solution again. Okay, I'm going to use a discrete circuit here. This is a discrete circuit. So remember that your alpha, your pulse here always refer, or the reference of this alpha is always at 0 second. Okay, so it will always refer to that particular 0 second here, or 0 degree. Okay, but you know that the thyristor 1, okay, thyristor 1 only trigger when you pass beyond that 30 degree, the commutation angle, isn't it? So we have the commutation angle where we have VR intersect with V blue. Okay, so we need to add this 30 degree to your phase control here. What we call it, alpha pulse here. Okay? So the gate signal, so the gate pulse here, we need to add 30 degree, and this is actually your alpha. 40 degree is your alpha. This is the commutation angle, because you want to make sure that it is shifted at 30 degree. Right? So we have all. If you look at the control signals here, is always plus 30 degree. Okay, it's always plus 30 degree for all thrusters. So again, we we start with a short pass. Okay, a short pass here. Okay, so 30 of so alpha is 40 42. So we have a short pass 40 42 for tester 1, tester 2, and tester 3. And now let's look at, now we have the conditions of alpha equals to 40 degree. Okay, alpha equals to 40 degree. I'm going to simulate that. Sure. Okay, let's look at the waveform now. Right, so this is waveform. So if I can draw quickly on the circuit. Okay, so this is thyristor red thyristor, this is yellow thyristor, thyristor blue connected to the resistor, then you have this ground. Okay, this is connected to the ground. So this is V red, V yellow, and V blue. Okay, so before this we have thyristor trigger from 0. So this is alpha equals to 0 up to this point where alpha equals to 30 degrees, right? So no problem, okay? No problem, because when we start at this point, we have call this blue. So this is the blue voltage. So blue voltage is the highest. Okay, so thyristor 3 or thyristor blue will keep on continue to conduct, and therefore voltage equals to blue voltage. The output voltage equals to blue voltage until you trigger at any time before your 30 degrees rate. Okay, and then you can trigger to thyristor red. Red. Okay, but now let's focus on this. Okay, so we have this thyristor 1 or thyristor R to start to trigger here. Okay, so thyristor red thyristor will start to fire there. Then again we have the R, the yellow, and the blue. Okay, so when we start to trigger thyristor R at this particular point, then thyristor R will start to conduct, and then the output voltage will copy the yellow phase, red phase voltage, isn't it? It will copy the red phase voltage. But then when it goes to beyond the negative cycle, so now your thyristors here experience the negative voltage, which is for reverse bias. it experiences a reverse bias, and yet you don't trigger thyristor yellow yet, isn't it? Because it has to wait to, which is 40 degree plus 120 degree. So this is 160 degree. But now you are actually at 150 degree there, isn't it? So there is no current flow, right? So thyristor red will be off, and the rest also will be off, and therefore there will be no current flow. Okay, current is 0, and therefore there will be no voltage drop at the resistor. Okay, so 0 voltage drop at the resistor, and that's why you have 0 voltage until you trigger thyristor yellow. Okay, because yellow at its highest potential, then you trigger thyristor at 160 degree, then you can see the voltage, output voltage connect to the yellow phase voltage just after 160 degree. Before that, then the voltage is 0, right? Because there is no current flow. There is nothing that forcing the thyristor red to turn on. Right? So all thyristor will be off, and that's why we have this discontinuous operation. Okay, so if we take this as one pulse, so let's consider this as a one pulse. Okay, so we know that this will be 0 degree, this will be minus pi over 3, and that will be pi over 3, isn't it? And that is 130 degree, which is 2 pi, 2 pi over 3, isn't it? 2 pi over 3. Okay, and if you look at from this point to that point, so the whole angle here will be 180 degree. 3. Okay, so if we split into 2, so from there to there, this is only 90 degree. And 90 degree, and this will be another 90 degree. Okay, alright, so now let's look at the monograph again, then note. Okay, so now we go back to the notes here. So as we switch or shift the waveform so that it will be at a peak at its 0 reference, then we have this as a, from that there will be 180 degree. Okay, from there to there is pi over 3. This is pi over 3. Okay, and this is 150 degree. There, there. Okay, so therefore, when we have the discontinuous operations, your limit will become, look at the limit now. So if you trigger thyristor yellow just now at minus pi over 3 plus pi, okay, oh sorry, your red phase, now we talk about red phase. So we have alpha minus pi over 3 plus alpha, so this become your angles now. Okay, we start to trigger the thyristor at this point, and it always stop at pi over 2, isn't it? The waveform is always stopped at pi over 2. So if you increase the alpha, then it become that, and then it will stop at this pi over 2. If you increase further, then your waveform become that, and then you increase further, and you have pi over 2. So that's why when you look at the integration now, it become 2 pi over 3, and then your limit of lower limit, you can minus pi over 3 plus alpha, and then the upper limit becomes pi over 2. Again, it is V peak cos theta d theta. Okay, so in between, I hope you can do it as an exercise. Please, please, you have to fill in the gaps and then try to find it. Try to prove that this is the output voltage in the end. Right? So we have two different equations for continuous and discontinuous operation for half wave rectifier with R purely resistive load condition. Okay, and again, derive the RMS load voltage. Okay? Don't just wait for me. So you have to do it yourself. Do it yourself, right? And try to find what is the RMS, the equation for the RMS load voltage. Because in the question, final exam, usually you'll be asked, what is the ripple factor? Example, what is a power factor? So you have to apply the same what we did for the single phase uncontrolled control rectifier to here. Okay, I'm not going to show you everything, but you need to find what is the RMS and then compare with the PC. Okay, result from PC to validate, to verify your equation. Right? So that is for the R purely resistive load. Okay, now let's continue with the half control rectifier with resistive inductive load. So what happens to the circuit if you have R plus L? Okay, so and here if you look at the waveform, we have a 40 degree, no, not a 40 degree. So the waveform here actually doesn't show the actual degree here. Okay, so I'm going to show you the simulation. Okay, so now this is simulation. I'm going to run it. So let's start with the 30 degree again. So let's say we have which is at the border, the border when the voltage touches the zero level. So I'm going to simulate that again. And let's look at the output voltage. And there you are. Okay, so the output voltage touches the zero level. Okay, at the border of 30 degree, alpha equals to 30 degree. But now look at the output current. Okay, so the output current now is continuous, isn't it? Because R plus L, because L is very large, continuous, then we have a continuous output current. Okay, so now let's look at if the alpha, the firing angle is beyond than 30 degree. Let's say 40 degree. Look at the output voltage now. Since there is still a current, so if I may draw the circuit again, okay, since there is a current, I'm going to just draw a constant current here. Since we have the current, so we have TR, T yellow, T blue here, connect to the voltage. Okay, right. So we know that before this, after 30 degree, what is it? This is the red phase, isn't it? So after 30 degree, okay, thyristor R will be off before this because there is no current at the output, isn't it? To turn on the thyristor. But now, since this is constantly, the output is constantly flow at the output, therefore it will force thyristor R to stays on, okay, even after 30 degrees here. So that's why the red phase voltage still continue to turn on. I mean the circuit here it is right. So we still have thyristor R to continue to flow even though the alpha is beyond the 30 degree. Still continue to flow to force the thyristor R to stays on until you trigger thyristor yellow there. Okay, and that's why you have a negative area now. So you have your output will become negative, and it is continuous. Okay, now it become continuous. The current doesn't have a discontinuous intermittent, so it become continuous all the time. All right, so that is the waveform. The voltage now becomes goes back to the same voltage as before equation. So we have minus pi over 3 plus alpha, and the upper limit become pi over 3 plus alpha all the time because of the continuous current output. So you will just follow the angle pi plus pi over 3 plus alpha. Okay, so this is your output voltage for the case of R plus L continuous current, right? Okay, so now let's continue with the effect of load and source inductance. This very much happens every time we discuss on the rectifier. In practical, again and again, we do have this source inductance. How they appear in the circuit, this is due to the cable or the transformer winding at the front end, right? So that's why we have this source inductance always appear in your circuit. All right, okay, so let me give us some revision on what we did in the uncontrolled version, right? So just that to the uncontrolled version. So we have LR, LY, LB for the diode, right? So we model as an ideal source. We remove this and we replace the constant current at the output so that we can focus on the effect of having the source inductance. Okay, so in this uncontrolled version, the overlap happens exactly as we transfer from the red to yellow current, isn't it? Which is happens after we have this 30-degree and this is 150 degree, isn't it? 150 degree. So immediately just after that 150 degree diode red diode will reduce and then diode red will increase. Okay, we have a fall of current from the red current, we have a rise of current for the yellow phase voltage, and because of that it will overlap. So both diodes will be on during this time. So for the control version, you actually just extend or just move that to the a bit to the front. Okay, so this is at for zero or diode zero. Diode happens. So if you think about the alpha, so the overlap will start at when we trigger the thyristor, isn't it? So it will start to have the overlap just after alpha. Okay, so now let's look at the notes again. Okay, so now we focus at the transfer of current red and yellow. So the alpha happens here. So this is where you start to trigger the thyristor yellow. Okay, so there is where you start to in reality, in practical, you have alpha equal to 130 degrees, right? Yeah. So we start to trigger thyristor R at alpha plus 130 degrees here. So just after that, then the overlap phenomena happens. And here we see that just after this alpha, then you see the output voltage is actually in between these two phase voltage, the red and yellow phase voltage, and the overlap uh, the output voltage during the overlap interval is actually in between both red and yellow phase voltage. Okay, so here we have because of the source inductance, the red current falls with a certain rate, and we have the current at yellow phase will rise at a certain rate. So both thyristors are on during this time. And now we're going to look at the equivalent circuit. So this is your output voltage now. So we have this missing area. Okay, we have a missing area here. So we need to consider this circuit again. So again we have that's the 1, that's the 2, that's the 3, and then we assume that we have a constant current at the output. Then we have source inductance, source inductance, and then let's connect back to your output. Okay, So now we have the thyristor 1 is on, this is on, so short circuit, and thyristor R also on, short circuit, but you don't have thyristor blue on. Okay, so this actually follow this loop. Going to have this particular loop here, isn't it? And this is your output VDC. Alright, so again we can assign this U current. U current is actually follow the yellow current just after the overlap. So we assign the commutation current, we call it a commutation current, that follow yellow phase current. Okay, so you have this loop, and then you do the overlap. During overlap, you have these two equations. Okay, add both equations. I hope this is very similar. I think this is very similar to the previous note. Okay, you just refer back to the previous note, and then you have this constant current. You need to differentiate constant current, get 0, and finally you find out that VDC, the output voltage during the overlap, is in between the average between red and yellow phase voltage, and that's why the instantaneous current of voltage equals to VR plus Vy divided by 2, the average. The usual the urban rate is equal to the average of two phase voltage. Let's say the overlap current is defined as IU, and now you sign the IU now, and then you do the KVL again. You have minus Vy plus 2Ls diu. Then you have this equation again, Vy equals to VR, and then you have integration. So the limit has to follow the whatever you have in the form. So it's actually starting alpha and it ends at alpha plus u. And look at the current, the input current. This is the input current, always from 0. I mean, for the half wave rectifier, three-phase rectifier is start from 0 to RDC. So it's very different to the single phase rectifier in terms of the limit. So you have to refer to the input current. This is your input current. So you integrate the yellow phase current here from 0 to IDC. Right? Okay. So that's why your limit become that. And then you solve that, and finally you find out that the overlap angle U equals to cos inverse cos alpha minus 2 omega minus ID divided by V peak line to line minus alpha. Okay, all right. So again, okay. So now we again for the output voltage equation, we always apply the same strategy. We know the output voltage without the source inductance, and then now we just simply find what is this average voltage drop here. Is it? Then we can simply subtract the equation that we had without the source inductance with this missing area here. Okay, so we just simply find the missing area, the voltage drop, and as well as the average of the voltage drop. So now you become alpha plus u. So if you take that Vy minus this equation, so if I can show you, this is your equation here, Vyt, and then you minus this equation, isn't it? So this equation actually obtained from the previous analysis. Okay, so that gives you that. Then you can find the missing area. Okay, and solve that. You equate with equation 1, and finally you find out that V drop equals to omega less IDC, and take the average. So you have to divide by 2 pi over 3, and finally the average voltage becomes 3 V peak line to line over 2 pi cos alpha minus 3 omega less ID over 2 pi. Alright, so again, here you need to look into the power factor as well. So the power factor can be found by this equation, like, okay, and always use the PSIM. I always encourage you to use PSIM. You must use PSIM because next video there will be assignment on using the PSIM to solve some problem related to the full wave rectifier, three-phase full wave control rectifier. So you must use the PSIM, and at this point of time, I believe you must have a we have seen a lot of equations, right? So it is better for you to put that in table. Isn't it? So you have this as the various circuits, single phase, half wave, R, for example. Then draw a circuit if you like. You can put in your words. Sorry, this is half wave. Okay, you make an effort, put in the word, right? You do it in the word processor, and draw this, and then you have V out. So what is the average equation for V out? You have V out RMS. Is that it? Write the equation. Just write the equation so that you can simply train your brain. You train your brain to identify which is which. Okay, so it will be a lot easier for you to extract the information if you are given if you put everything in the table, right, from the table, so you can relate one circuit to another circuit, so you can train your brain to easily to get easily extracted to easily extract the information, the equation from the table. Okay, so that's it. And smoothing, yes, if you want to smooth the output voltage, what you need to do is just implement the three-phase full wave rectifier that we're going to discuss on next video. Okay, so again, there's a lot of past exam question on the single phase control rectifier. Please do it, and then always ask me from using that Padlet, my chat on Padlet. Okay, I always welcome it anytime. Inshallah, I will answer that. Okay, right? Okay, thank you. Assalamualaikum.